folks, so for this lesson we're going to be talking about how to characterize motion that's moving at a constant rate. And in order to do that, we're going to introduce two new terms for you, speed and velocity, and talk about different ways to think about speed and velocity. So let's get started. Okay. So we already saw before that if we take an object moving at a steady rate, like our battery-powered cars, and we make a graph of their displacement versus their time, we get a linear pattern where the slope represents the object's velocity. So our best fit line for that data will end up giving us the formula displacement is equal to velocity times time. Now, we talked about this in class, but we haven't actually defined velocity yet, other than it has something to do with how fast the object is moving. So let's slow down for a minute and talk about velocity. All right, so you probably don't normally use the term velocity in your everyday life. You're more likely to talk about speed, and they're similar, but with some slight nuanced differences. Okay, so speed you probably know of as the rate of distance traveled over time. So how far can you go per second, or per hour, or per year, some unit of time. Okay. Now, velocity is similar. It's the rate of displacement over time. And so for our last lesson, we talked about that difference between distance and displacement, where displacement is how far you are from where you started, whereas distance is just how far you've traveled in total with all the little roundabouts and detours and everything on your route. Okay, so a couple distinctions then to note between speed and velocity. Velocity includes speed, it includes that rate of travel, but it also then includes direction because displacement includes direction. Another key thing to note about velocity is that it can be positive or negative because that negative tells us something about the direction. So if we've got a velocity going to the south, a way to distinguish it from a velocity directed to the north might be to say that it's a negative velocity. Now pause for just a moment and check in. We talked last time about the idea of scalar quantities and vector quantities. So take a moment to answer for yourself. Based on this, would speed be a scalar or a vector? Would velocity be a scalar or a vector? Now it turns out alliteration is working pretty well for us here because it turns out that speed is a scalar because we're just looking for a measurement, some number of meters per second. We don't care about the direction, whereas velocity, we do care about direction, so velocity is a vector quantity. Speed's a scalar, velocity is a vector. Okay. Now if we want to write a nice formula for this, we can have this formula right here, which is basically the same as our equation from our graph before, just rearranged a little bit to put velocity by itself on one side of the equation. So the average velocity of an object that is moving is just equal to its displacement or change in position over time. And our default units to use for a velocity would be meters per second, since our standard unit for measuring displacement is meters, and standard unit of measurement for time is seconds. So let's try this out really quickly. Say we've got someone who's driving a car with an average velocity of 48 kilometers per hour to the east. We want to figure out how long it's going to take to drive 144,000 meters along a nice straight highway. So my first recommendation is make a list of everything we know from this problem, all those numbers that you see in there with their units and what variables they represent. So one number that I see here is 48 kilometers per hour. And when I see 48 kilometers per hour, I know that's a velocity because it's a measure of displacement over time, kilometers per hour. So that's my average velocity for this problem. And then I see 144,000 meters. Now what's measured in meters is displacement. So that tells me the displacement of this driver. And so that's all the information that's given to me. I'm trying to solve for time. Now, before we jump right into our equation, we got to slow down a sec. Take a moment to try to identify what is it we need to do first before we can just start to plug and chug. So a big red flag for me is the fact that my velocity and my displacement are using two different units of measurement. I've got average velocity in kilometers per hour, but displacement's in meters. I have to make those match before I can start using any of my equations. So I'm going to go ahead and convert that velocity into meters per hour instead. Now, since there are 1,000 meters in a kilometer, I just need to multiply by 1,000, and I determine that the average velocity is 48,000 meters per hour. Now all my units match, I'm ready to go. So I've got this equation, displacement is equal to average velocity times time, or I can rearrange that and divide both sides by that average velocity to get time is equal to displacement over average velocity. And then I just go ahead and plug everything in. I've got a displacement of 144,000 meters, velocity of 48,000 meters per hour, and I determine that it will take Simpson 3 hours to drive that displacement. Cool. All right. Now, one thing you might notice is that I've been specifying average velocity, because the thing is, things don't always move at a consistent rate the entire way. And you might have even noticed that with your battery-powered cars, that sometimes they'd speed up a little bit, they'd slow down a little bit, they get stuck on something. And so that allows us then, or that requires us to draw a distinction between different ways of measuring an object's velocity as it's moving along. So one way we can think about velocity is this idea of instantaneous velocity. Now, instantaneous velocity is just how fast are you moving right this second, right this instant, hence the name instantaneous velocity. So if we were to look at the instantaneous velocity of your battery-powered car, it might be higher at one moment and then a little bit lower at another moment as it speeds up and slows down a little bit. Okay. Average velocity, on the other hand, is often easier for us to calculate because we don't worry about all those little dips and peaks and everything, all the little changes in velocity. Average velocity just tells us overall, what was the average for the entire time? What was your total displacement? What does the total time it took you to get there? And then we just divide those two. Okay? So basically what that average velocity is telling us is if your battery-powered car weren't speeding up and slowing down and getting a little bit faster and slower along the way, what constant velocity could it have maintained to still arrive at the same location in the same amount of time? Right. Now, one thing that might make this easier to think about is by graphing, so we can visualize how this works. So say we've got a motion that looks like what you see in this graph right here, where the position is increasing steadily for some period of time, so we see that this object is moving at a constant velocity, and then we level out for a bit, and then it goes down again. So if I wanted to figure out the instantaneous velocity at any point, all I need to do is figure out what is the slope of the line at that particular point in the graph, okay? So for example, maybe we want to figure out instantaneous velocity at 5 seconds. So I see here I've got 3 different ranges, 3 distinct periods within this graph. If I try to identify where the 5-second point is here, I can see that that's falling within region 3. Okay, and so all I need to do is figure out the slope of the graph during region 3. I don't care about region 1. I don't care about region 2 because those don't have anything to do with how fast the car is moving during region 3. So for instantaneous velocity, I'm only looking at the slope of one particular part of the graph. So if I want to figure out the slope of the graph during region 3, I'm going to go ahead and figure out the change in position during that time, which I see it went from 6 meters down to 4 meters, so that's minus 2 meters. It went backwards 2 meters. And then the amount of time it took to go back those 2 meters for region 3 is 2 seconds. It took from 4 to 6 seconds. So then I can determine during region 3 of this motion, from 4 to 6 seconds, that instantaneous velocity during that time period was negative 1 meter per second because it traveled back 2 meters over the course of 2 seconds. Okay. So that's instantaneous velocity, just figuring out the slope of a particular region, a little part of the graph. Now, if I wanted to figure out the average velocity for this whole journey, on the other hand, what I would do is draw a line from my starting point to my ending point, because I'm just trying to figure out total displacement, total time. I don't care about all the little bits and pieces where it's faster, slower, etc. It's just overall, what was that average velocity there? Okay, so I'm going to go ahead and draw a line from the starting point to the ending point of my graph. Now I just need to figure out the slope of this line, and I've got the average velocity. So to figure out the slope, we'll look at the change in position. It starts at 2 meters, it ends at 4 meters, so that's a change in position of positive 2 meters. And the time it took from start to finish was 6 seconds. So then the average velocity for this motion is 2 meters over 6 seconds, or in other words, 0.33 meters per second. So let's take a moment just to check in, make sure that we've kind of got this distinction here. So some of you may be driving, or maybe you're not driving, but you've taken a little peek at the dashboard while someone else is driving, and you've maybe seen the speedometer that's telling you how fast you're going. One question for you to consider is, should that speedometer actually be called a velocimeter? Is it misnamed? Now the answer to that question is, well, no, it doesn't give a direction. It just tells you how fast you're going. And if it just tells you how fast you're going and doesn't give you a direction, then we know that that must actually be just the speed, not the velocity. It's a scalar, not a vector. Second question is, does that speedometer tell you your average speed or your instantaneous speed? The speedometer gives you an instantaneous reading because it's telling you how fast you're going at that particular moment in time. We see it go up, go down as you hit the gas and as you hit the brakes. All right, that's it, folks. Hope that helps clarify your understanding of speed and velocity.